Hello, everyone. Sometime back, somebody requested that I go over threading in PySide, and I thought, this is a good idea. This is a topic that sometimes people cover, and they cover fairly well, and sometimes they don't. So let's begin with talking about why we need to thread an operation to begin with, and why does threading keep our GUI responsive? So what I'm going to do, we're going to take a look at this small application here. I'm going to run this. This is something that a beginner in Qt may actually start with. Nothing too complicated. When we hit the start button, we're going to start increasing a counter here. So we're going to have 1 and 2 and 3, 3 and 4. Oops, 4. Nothing really too earth-shattering. So let's take a look at the code. Our QMain window is pretty self-explanatory. There's nothing too interesting here. We just set some buttons. And then when we click the Start button, we're going to call this function called onStart, which is going to take the Start button and disable it, the Stop button and enable it. We're going to set a status message saying processing. Our continue run flag is going to be set to true. And then we get into this loop for I in range 100,000. If the continue run flag is true, then we're going to set the result of the counter inside this line entry. Sleep for a small period of time. If it's done or somebody clicks the stop button, we will say show message stopped, flip the buttons, or when we're done, we'll flip the buttons, and then we'll say status show message equals finished. Nothing too earth-shattering here. If you hit the stop button, it will take and set the continue run to false and then flip the buttons. And our main is almost nothing. Okay, so let's go ahead and run this and let's see what happens. I hit the start button and it doesn't appear that anything happens. Um, yeah, well, in actuality, stuff is actually going on in the background. The problem is that everything seems to be frozen. If I hit the close on the window, it should go to, yep, not responding. My window manager should, yep, right on cue, saying, hey, it's not responding. Do you want to kill it? Sure, let's kill it. Okay, so we need to have a discussion here as to why is this happening. So the first thing that you might do in trying to troubleshoot something like this is put it into debug. And I've got a breakpoint set here already. So I'm going to hit debug. I'm going to hit my start button. And yes, we are actually going into the onStart function. If I start stepping through, the button should be flipping. There should be a status message saying processing. However, when I look at this, there's nothing here. The buttons did not flip. The counter or the message is not showing. If I continue to go through the loop, I'm setting the line entry. This line entry should have data in it, and it doesn't. Nope, nothing. Okay. The reason that this is happening is because when you are new to Qt or new to PySide, I usually try and say PySide, but Qt, it's the same thing. The problem that's actually occurring here is a misunderstanding when we are running these types of code where we are actually setting text in a line entry or we are trying to flip buttons around, we're trying to put a status message. We actually may look at this and say, well, isn't this being ran directly? The answer is no. None of this code is actually being ran directly. What is happening in the background is when I run this type of, specifically this type of type or line of code, is that it is putting an event inside something known as the event queue. And people who are new to Qt may look at this and go, well, where's the event queue? I don't remember creating an event queue. I don't remember starting an event queue. None of that. Well, actually, you did. When we come down here to our main function that runs when we start this application, we are creating a queue application. We are creating a main window. And then we are starting the event loop with app.execute. So everything that we do with the GUI puts an event in the event queue, and it's this line of code that actually processes the event queue. Now, if you want to see that in action, it's not that hard. What we'll do is we'll reduce the amount of loop here, and we'll put this into debug again. I'll hit start, and you'll see we're back at this line of code. I'll start stepping. Okay, we're going to run those lines, and then we are going to return. So if you take a look at this application now, nothing has changed on it. Nothing in the counter, the buttons didn't flip. Well, they'd be flipped back now, but nothing in the counter, no status message, nothing. However, watch very closely when I step over this. Look where I went back to. I went right back to the app.execute. This is going to process events that are now out there hanging in the event queue. So if I go step over and we look at the window, now we got stuff. And that's because everything that was piled up and stuck in the event queue was suddenly processed. Here's a good way of thinking about this. Let me do a drawing for you. And let's see, general and flowchart. Okay. So here's a real world example for you. Let's say that you land up at the grocery store. And I'm sure all of us have gone grocery shopping at least once. This is our checkout lane. And let's say that you show up at the grocery store and you only need a couple of items. However, you pick up your couple of items, and right before you get into the line, here comes this guy with 2 full carts of groceries. So now you are back here with your couple of items, and this guy is now ahead of you with 2 full cartloads. That's what's happening here when I'm running this application. Because I have this giant loop that I am stuck in, none of the events in the event queue can process. So if you think about it, this is me. I am the event queue. I'm waiting for this guy to finish. So I'm not going to process, or I'm not going to be able to check out in my grocery store analogy here until this guy with 2 full carts is completely done. And that's why we are stuck. It's because we are blocking the event queue from running. All right, so the rest of this video is going to be going over how we solve that problem. And the first thing I'm going to show you is a bit of a hack. So I actually don't recommend that you do this. Where did I put it? Here we go. This line of code here, where we would put this, and I'm going to increase this again. Where we would put that is right here. Now, this line of code is saying for the event queue that's in this particular thread, which is the main thread, we haven't created any others yet, pardon me, for this line of code that's in the main thread, go ahead and process all of the events that are stuck in the event queue. So let's go ahead and run this again. And when I hit start, you'll see that things actually worked. So the start button disabled, the stop button enabled, I got my message, and my counter is counting up. But you'll see the counter is a little bit shaky, a little bit jerky, and that's just the nature of the beast. But when I hit stop, we actually stop. So that might, well, you might be tempted to say is, oh, great, problem solved. Well, there's a slight problem with this, and that's that Qt does not recommend that we employ this method anymore. So if you're listening with one ear open, what I would highly recommend is if you come across old material, old videos, old Stack Overflow posts, those types of things, and they recommend doing it this way, don't. Okay, this is not the preferred solution today. But I wanted to show it to you because sometimes you run across these things in older material. Okay, so we got to think about how are we going to solve this? Well, let's go back to our grocery store analogy. What would be the best way to solve this? The best way to do it would be for the store to come to its senses. Actually, I'm going to copy and paste this. The best thing to do would be for the store to open up another checkout lane. And then we take Mr. Two Carts here and we move him up here, and then we can go through the line quickly. And this is exactly what we are doing when we are employing threads in PySide. We are opening up another checkout lane. We are starting another thread that we can put work into. And if you think about this being your GUI thread and this being your secondary thread, the two of them talk to each other through the use of signals and slots. All right, so how do we do that? All right, first off, we're going to look at what I like to call the more traditional method for threading. This is far older than some of the other methods, but this is the method that I generally employ quite a bit. And the first thing that we're going to do is we are going to create an object called worker that is based off of QObject. Then what we are going to do is we are going to define two signals. The result is going to be the result of the counter, and this is what we are going to emit out back to Q main window, and we're passing an integer. And then we have a finished signal, which is going to pass a string. Then we define our continue run flag. And then we have a slot, which is over a function. This is our slot decorator called run worker. And so this is what's going to be called. And I'll show you how we call that here in a few minutes. Everything else is basically the same, except instead of trying to update the GUI directly, which isn't going to work, we take self, right up here, self.result.emit. So every time the counter increases, we emit that signal back to our main window. That's what will actually update the GUI. And this is very, very important for you to understand. When it comes to starting workers like this, and when it comes to getting the results or the work that a worker is doing, you must use signals and slots. There are a couple of exceptions to this. I'm going to show you that here when we go to stop this worker. I do it directly, and I will tell you why in a moment. All right, then in our main window, we've got a lot more setup here. But the first thing we do is we define a signal called start worker. And that's going to be emitted to our worker to tell it, hey, go ahead and start running this run worker. Next thing we're going to do, besides our usual buttons and stuff, is set up a thread and a worker. So we create a thread, and then we create a worker. And this worker is based off of the custom worker that we just defined above. Then we do worker.move to thread. Then we connect the signals and slots. So our start worker gets connected to self.worker.run worker. Our worker.result gets connected to self update result, and then our worker finished gets connected to self.worker finished. And then we start the thread. Starting the thread does not automatically start the worker in this case. I want you to remember that. Starting the worker does, or starting the thread does not automatically start the worker. It's when we emit this signal that that's going to happen. And these steps here, this is the order that you need to do them in. Very important. Create your thread, create your worker, move the worker to the thread, connect your signal slots, and then go ahead and start the thread. So when we start this thread, we are going to have a worker sitting in another thread waiting for work to be sent to it, or a signal that tells it go ahead and begin processing. Okay, so on our start, which is connected to our start button, we will flip the buttons again, we'll show a status message, and then we will emit that signal. So self.start worker emit. And I'm not passing any data here. I'm just telling it to go ahead and start. The update result. So the worker and the GUI thread work in tandem with each other. When the worker emits the result of the counter, it will call this function, and that will actually put the line entry result and set it to the result. So instead of trying to do it directly, the worker emits that signal, it gets sent here, we pick it up, and then the GUI thread actually sets the results. And because that's happening, it can go back to app.execute and actually process that event. There's no giant loop. It's not stuck in some big loop, and the worker's what's in the loop. On stop. So when I click the stop button, what is going to happen? I am going to reach directly into the worker, and I'm going to take that continue run and set it to false. Now you may say, okay, you just said that communication between worker and main thread, GUI thread, should be done through signals and slots. That is correct. However, if I want this flag to be flipped, if I were to create a function and send it a signal to stop, you look at this worker, because it's based on QObject and we're running it in a standard run-of-the-mill Q thread, it has its own event loop. So if I were to send it a signal, it would have to finish this loop in order to be able to process that event. It would be stuck on this thread's event queue. So that's why I actually reach in here directly and do it. Now you may say, well, what's going to happen if I were to try and start the worker by calling run worker directly? If you were to do that on start, if I was to, instead of emit this signal, what if I called it directly? Well, it is going to run in the thread from which it was called from. Because I'm calling that in the main thread, it's going to run it in the main thread. So that's why I have to send it a signal in order to start when it's running in a secondary thread. So I can't call that directly, but in order to stop it, I can actually call it directly. And then when the worker's finished, it's going to emit a signal which is connected to this slot. It's going to take a message, and we're going to show that status message. Now, what if we hit the exit button or we close the window? So that's why I have overridden the close event. I don't want to just process events from the exit button. I need to process events, or not process events. I need to do things when somebody closes this window. So first off, if the worker is actually doing something, I'm going to reach into the worker and set the continue run to false. That will stop the worker from continuing any work. Then I'm going to issue a self.thread.quit and then self.thread.wait. This quit will actually shut the thread down, close down its event loop, and then we issue a wait just to make sure that that actually finishes. And then if if this window was not standalone, in other words, I opened it from another window, I want to also issue a worker.deleteLater and a thread.deleteLater. I don't have to do this if this application is totally self-contained, like this one is. This is a one-window app. However, I put these in here just for templating's sake, really. Okay, and then we can run it. So what happens this time? I hit start, and everything starts normally. You'll see the counter is actually very, very smooth. If I hit stop, everything stops. If I start it and it's running when I hit the exit button, everything closes just fine. If it's running and I hit the close window, it stops normally. So how can I tell if I'm running in a secondary thread? Well, it's actually pretty easy. What you can do is just add a breakpoint and put it into debug. So if I go into debug and we step, oh yeah, you actually have to do something. Hit start. Okay, there we go. See this over here that says dummy? This is my secondary thread. Now, how does it look if I'm in a main thread? If I am in a main thread, debug, you'll see it will say main thread. So, pretty easy to tell if I'm actually running in a secondary thread or I'm running in a main thread. Okay, that covers the basics of method number one. Method number two. This is using something called QRunnable. It is a lightweight container to be able to run in a secondary thread. And unlike the traditional method, as I like to call it, unlike the traditional method, Qt actually does some of the work for us in this case. Now, when we define a worker that is going to be based on QRunnable, the first thing that we have to remember is that QRunnable is not based off of QObject. QRunnable does not inherit from QObject. So what that means is that I have to create another class called worker signals based off of QObject so that I can hold the result from the counter and then the finish signal. So whereas before, the worker that I used in the previous example, that is based off of QObject. QRunnable is not. So first things first, we create a new class called worker signals, and we define our signals in there. All right, then we can define our worker. And first thing I do is I create my signals object based on worker signals, and I set my continue run to false again. All right, now this is where QRunnable differs from the traditional method pretty dramatically. One is, in the previous example, I had the function called runWorker. In QRunnable, the function that you create here must be called run. You see, I even put a note here. Must be called run, and you'll see it's overridden. See, overrides method in QRunnable. I don't have a choice. I have to name this run. All right, everything else is in here is exactly the same as the previous example. Our main window, though, there's a lot less setup. The only thing we're doing here in the initialization method for our main window is we are creating a thread pool. So I create a self.thread pool based off of QThreadPool. Everything else is exactly the same. Now on start, this is when we push the start button. things are a little different. I'm still flipping the buttons, showing a message, but this is when I'm creating my worker. I create my worker, I set my signals, I connect my signals and slots just like we did before, but remember, this time it's not just worker.result, it's worker.signals.result. It's worker.signals.finished. So instead of just worker.finished. Then what I do is I do self.threadpool.start and I tell it, here, start this worker. So instead of having to emit a signal to start that worker, all I do is say threadpool.start self.worker. What Qt does under the covers is it goes out and gets a thread from the thread pool, puts the worker inside of it, starts it, and automatically runs that run function or run method inside that worker. So there's a little bit less boilerplate code running a Q runnable than there is just doing a standard Q thread. All right, we have our update result. This is the result from the worker. And then on stop, I still reach in and go worker.continue run equals false, flip my buttons. My worker finished, I show my message. Close event is a little bit different. I need to check if I have a worker. If I do, I set that run flag to false. And then all I have to do is say self.threadpool.wait for done. And then I can close the window. This is very important to remember. When it comes to a Q runnable, when this run function reaches its returns and it finishes, that particular worker is done for. So there are some hoops you can jump through. I've seen example code, although I don't really recommend doing it. I have seen some example code where people try to keep a Q runnable open. To me, this is foolish. This is meant for, Q runnable is meant for set it, forget it type deals. All right, so let's say I'm going to send out an email. I'm going to consume a web service. They're not things that you would be running over and over and over again. All right, so let's go ahead and run this. And you'll see we get the exact same result. When I hit stop, everything stops. If I'm running and I close the window, everything stops. So, when do I use one versus the other? Well, the regular or the older method, the traditional method, does have a few advantages in the fact that you can have a worker sitting out there waiting for work. And this comes in handy in, especially I use it quite a bit for database operations, where you might be fetching a bunch of database records over and over and over again. In fact, I've got an example where I'll show you that. Q runnable is, like I said, more of the set it, forget it type thing. Not something that you would run continuously or constantly, but something where, hey, I'm going to lock up my GUI if I don't push it somewhere, and I don't want my GUI to freeze, for instance, in, let's say you're going to send an email or you're building a spreadsheet every once in a while. That could lock up your GUI quite a bit. So you create a Q runnable and push that work into there. There's less work to do here simply because there's less boilerplate code. I don't have to create my worker, create my thread, move my worker to the thread, start the thread. Stopping is much easier. But it's all up on the question really is, what are you going to be doing, or what do you need to offload? Is it something you're going to call quite frequently, or is it something that is going to lock up your GUI, but you're not going to be running it constantly? All right, let's take a look at another example. And when I run this, what I'm going to be doing is I'm going to be generating SHA-256 checksums for all the files that I find in a root directory. So let's go ahead and run this with my home directory. Or not with my home, but with my desktop. And so you see everything on my desktop, I only have a handful, actually generates a 256 checksum for me. Um, this is where proper testing comes in because this is not threaded, but you'll see that it looked like it ran correctly. So if I'm hitting the start button, you'll see that I am populating the console with print messages and I am running this. It does look to be running correctly. However, where it gets interesting is when I try to process a much larger directory with a lot more files in it. So let me run this. Mount backup VMs Minecraft. Let's run the backup of my Minecraft server. Ah, now we're locked up again. And the real question is, why are we locked up again? Well, it's actually the same reason as before, and that is because we are stuck in a loop processing all of this, and you'll see that my GUI is not updating. That's because all of the events that are happening in that code are actually piling up in the event queue. So flipping these buttons, clearing this table, populating this table, it's all stuck in the event queue. And when this finishes, which I'm going to go ahead and stop it because I think I put a slight delay in here. Did I put a delay in here? No, I didn't. Darn, I should have let it just finish. Okay, anyway, we're stuck in the same problem, which is this isn't threaded. And depending on the size of the directory or even the size of the file, it's not going to work. That's because we can't process events in the event queue. And to show this even worse, I'm going to go mount backup VMs and then images. This is where I store the backups of my virtual machine's disk images. Now it really looks like nothing's happening. And that's because what's in there are very large files. They're disk images for virtual machines. So it's going to take a while to go ahead and process all of that. Every one of those files is big. So it's not going to show anything up on this window until all that's done. And it's just way too big. So let's go ahead and stop it. All right. So how do we solve this again? Well, we do threading. And I'm going to show you the traditional threaded model through the rest of these examples. So adapting this to use QRunnable is not really that difficult, but I'm going to stick with the traditional method for the rest of the examples. So again, I have a worker, I have my signals, my continue run flag again, and then this process directory is what is going to be called when we emit that signal. Don't worry too much about the code in here. It's not really that important. It's just this is a long-running operation that would lock up the GUI. Then again, in our main window, we have start worker. Now, here's where we need to have a discussion about views and tables. So you'll notice that this application, and I can run it for you really quick, this is actually using the widget QTableView. And in the background, it is using a widget called QStandardItemModel. If you are unfamiliar with this whole model view architecture, go ahead and get rid of our people here. So let's say you have a data source, for instance, a database, Go figure. People store data in databases? Yeah, I know. Go figure. The first thing that we do is we have something called the model. And the model actually is what is populated first. So in our case, we are going to be using Q standard item model, and you'll see later on why that's not always the best option, but we'll get there. The other one we use is Q abstract table model. And apparently, I'm going to make that a little bigger. Okay. And then what actually shows this data is Q table view. Yeah, there we go. Okay, so this is Qt's implementation of model view architecture, where I take the data from a data source. In the example that we are looking at right now, that data source is the checksums that we're generating and emitting out. I put them into a model, and I've got two different options to choose from. And then showing that data is QTableView. Now you may think, well, what about QTableWidget? Okay, let's talk about QTableWidget. QTableWidget is the next up from something that we used to have called QTable. QTable is now long obsolete. And QTableWidget isn't exactly too far behind it. There was no model in between, but what actually is happening under the covers is QTableWidget is wrapping everything that you put in a cell in a QTable item, which is something that you normally don't call directly. It's all done under the covers. The problem is QTableWidget, when you're talking about wrapping each individual cell in a Qt object, when you get over 100,000 rows, this thing tends to choke out because it's memory intensive. And that's one of the reasons why I want to talk about these two models here. The Q standard item model is fairly easy to use. Its drawback is it is very memory intensive. And I'll show you an example of that. Q abstract table model, you have a much, much lower footprint when it comes to putting in data, except it's a bit of a pain in the patoot to set up. It's something I really don't like, but it does work once you get it all set up. Okay, so what we're going to do here is we're going to set up a model, which is a Q standard item model, tell it the columns, and set our horizontal header labels to file and hash. Set up the table view. So I created a table view in Qt Designer, where I design all my interfaces. And I say set the model to the model that we just created. Then I say edit triggers, no edit triggers, and set the selection behavior to select rows. Set up our buttons. Then we set up a thread, set up a worker. We move the worker to the thread. Then we connect our signals and slots. And in this particular case, we've got worker.process directory. That's what's going to start the worker for us. Worker.result is connected to add row to model. Worker.message is sent to show message, and then worker finished is set to worker finished. Start the thread. So when I click the start button, the first thing I'm going to do is to validate the directory that I'm going to process. So what that means is if I go and put garbage in here and hit enter, it's going to tell me that it's an invalid directory. Nothing too earth-shattering there. Then I'm going to go ahead and clear the model in case we had data inside of it. I'm removing the rows. Let's see, we created directory, which is a path object. And then I do start the worker emitting the directory and saying that this is at the root level. And that's just because of all the recursion that goes on in that worker. Validate directory I covered. On stop, I reach right in the worker and I say continue run equals false. Flip the buttons. Now, the result from the worker, the item name, the file name, and the item hash, the file hash, I need to add that row to the model. So when that signal is emitted from the worker, it comes here inside the GUI thread. So again, this is like cooperative processing. Why am I not doing this? There we go. So this is like cooperative processing. Here's my worker. And here is my GUI. Okay, and the worker emits to the GUI. Now that does not mean that the GUI thread, the main thread, is doing nothing. And this is something that you need to keep in mind when it comes to performance, because there are situations where your worker may emit things out so fast that your GUI thread, your main thread, can't keep up. Because when you emit that signal and you call that add row to model, that is the work of adding to the model is being done in the main thread. So there are some performance considerations to think about here, and I'll show you some examples. So we have to create a row, which is a list, and each item that we add has to be wrapped in a Q standard item. And this is where this tends to get a little bit memory intensive. And then also we have self.model.append row. That's pretty self-explanatory. And then at the end here, we're going to be resizing the columns to contents. Makes perfect sense. Show message, that will actually put a message in the status bar. Worker finished, we show a message and then we flip the buttons again. Close event is exactly the same. So I make sure to stop the worker if it's running. I quit the thread, wait for the thread to quit, and then delete later the worker and the thread. Okay, let's go ahead and run this and see what the difference looks like. I'm going to check, before I do that, I'm going to go up here and check my worker for one thing. Yep, okay. So let's do my home and my desktop again. Okay, that worked fairly fine. Of course, it worked fine in the non-threaded example, so let's try to do boot. Yep, that worked okay. And you'll see there was a flash of the messages down there, but GUI stayed responsive. Table is all nicely populated. Let's try my Minecraft directory. So mount, backup, reends, Minecraft. Okay, little different. Oh, but now we got a problem again. You notice that the messages were coming in okay, but now they seem to be stuck. Now the prints down here in the terminal are working fine, but what's going on with this? Well, it's like I said a few minutes ago. We are literally bogging down the GUI, but we've got to investigate where are we bogging down the GUI? Because if you're looking at this, it looks like the GUI is actually running slow. In fact, you probably can't hear it, but my PC fan is is actually ramping up a little bit. And you'll notice too that I can't scroll. I should be able to scroll here. Oh, now I scrolled. Oh, that's interesting. So we're still processing events in the event queue, but it's bogged down. Let me hit stop. Oh, it finished. Okay. I know what the problem is. I have experienced this, but what is it? All right. Remember when we did this add row to model? Okay, look what we're actually doing here. Let's go over this again. We create the row list, which is the two standard Q standard item objects. We add it to the model, and then we're running this self.resize column to contents. Technically, we are doing that every single time we add a row. That resize column to contents operation is extremely expensive. So if you have like 5 or 6 rows, it's not too bad. But when you start getting into the couple of dozen, the hundreds, it's running this every single time we add a row. And that's why the GUI is so bogged down. So let's fix that with this option here. Okay, so we're just doing creating the row and doing self.model.append rows. And then when the worker is finished, that's when we do the resize columns to contents. We show the message, flip the buttons, that type of thing. So let's see how this one runs. Backup VMs, Minecraft. Oh, look at the messages. Oh, and we're already done. So not too bad. And what happened is it populated everything. If I run it again, see the table clears and it's already finished. So just by removing the resize until the end, it improved the performance of this dramatically. And that's because I'm not bogging down the GUI thread. The GUI thread is keeping up with the worker that is spitting out all of these files and hashes. Now, what happens if I do my images? See, now you'll see I did get a message down here that I am processing this file. And this is why I send a message out every time I start to process a file. Because if I didn't have that visual feedback, the start button's grayed out, but it looks like it's doing nothing. So that's why I send a message out that says, hey, I'm actually processing this file. And if we wait here a little bit, it will actually show up here, but I'm not going to wait. I'm just going to tell it to stop. And see, when I hit stop, it stops loading instantly. Okay. Let's look at that again, except this time I've done one big thing that's different. So instead of using Q standard item model, I am now using Q abstract model. And Q abstract table model has to be subclassed. It's one of the things that makes it more of a pain to use, but that's just part of its charm. So I create this class called hash table model based off of Q abstract table model. And let's see, I'm not going to get into too much detail with this thing, but the main reason why I am using this versus using Q standard item model is because the memory footprint is so much lower. Otherwise, the threading here is exactly the same as in the previous example. And you will actually see a bit of a performance boost here, although not much there. If we do mount backup VMs, Minecraft, it plows through that pretty quickly. So there is a bit of a performance boost when using Q abstract table model because, number one, it doesn't have to wrap each one of those cells in a Q standard item. There's a lot that's actually going on in the background when that happens. So it eats up resources inside your GUI thread. Not only that, but it takes up a lot more memory. Otherwise, works exactly the same. All right, now let's take a look at an example where instead of generating, we're actually reading from a MySQL database. So I have got this context table here in my testing database, and I populated this with 100,000 records. It's all fake. It's all generated using the Python library Faker. So if you've never used Faker, it's really great for generating this kind of stuff. Otherwise, I'm never going to have 100,000 contacts. So worked out pretty well for me. All right, so what is different about this? Well, we are going to be fetching data from a database. And there are considerations we need to think about when we are going to be threading that type of operation. One is database connections. It is not generally a good idea to share a database connection between two threads. That can cause a massive amount of problems, especially if you're both trying to do database operations at the same time. So, like in MySQL, I run a MySQL instance here. What they offer us is connection pooling. So in the beginning of opening this window, we are going to be creating a connection pool with two connections. And I just use my testing user. And then what I do is I return that database pool. And this is if I just call it directly, but this is very important. You do not want to open up a database connection in one thread and then pass that to another thread to use. Big fat no-no. Don't do that. Use connection pooling. So every time my worker is going to run, it's going to grab a connection from the connection pool. When it closes that connection, it's not actually closing, it's returning it back to the pool. Okay, so here's my database worker based on QObject. And first thing I've got for signals is headers fetched, which is the column names, row fetched, which is the rows, and finished when I'm done. I have a continue run flag again. Then I have a function called fetch database rows. This is what is going to be called. Set the continue run to true. Then I do some trying here. I have my database connection is pool.getConnection. Open up my cursor, get and emit the column names, get a row count. If I don't have any rows, I want to get out of here. Get and emit the rows. I set up my SQL statement for row and cursor. Now, this is important. In this first example here, I am actually reading this table one row at a time, and then I am emitting that row to the GUI thread, the main thread. This isn't the best idea, and we'll get into that in a little bit here. When we're done, we close the connection, or close the cursor, close the connection, emit the finished signal, and if we have an error, we emit that too. Okay, so My Q main window is basically the same. I set up a model, which is a Q standard item model in this case, set up a table view, and set up my thread and worker just like we did before. Connect the signals in the slots, start the thread, show the window. On the load, I'm going to be emitting the start worker. I'm going to be emitting this signal, start worker, and I'm passing that pool connection. Then the worker will grab from the pool, process all the records, and then show them here. This is different. We're going to add the headers to the model, and that's what that code does, and then add row to the model. And you'll notice that this time I had enough sense to not resize the columns to contents. Worker finished, we resize the column to contents. Close event is exactly the same. All right, so let's go ahead and run this. I'll show you how this works. I hit load, it fetches the context, and then at the end, it resizes the columns to contents. Not too bad, right? I'm going to hit load again to refresh it. Ooh, what happened? Yeah, I've got another problem. And this is something that I wanted to point out to you. I did this on purpose. And my PC fans are going bananas. Where's the problem? Why did it lock up this time? Because shouldn't it just be telling the worker to do the work? Well, on load. Here's our problem. Self.model.clear. Now you would think, why would clearing a Q standard item model be such an expensive operation? The answer is I have absolutely no idea. But when you issue a model.clear on a Q standard item model, and it is big, where ours is populated with 100,000 records, it takes forever to clear it. And clearing the model removes the headers, and it also removes the rows, the data. So why this is such a expensive operation beats me. It seems logical. You would just go ahead and clear the model. However, it doesn't work very well. So how we improve the performance is instead of model.clear, we do model.remove rows, starting at the first with the row count. And believe it or not, this is much, much faster. Okay, so now it's loaded. So now I'm going to hit load again. And you'll see it cleared really fast and then called our worker. Our worker fetched the records. And as they're emitted, they're being put into the Q standard item model. So nothing too hard there. Let's look at the last example. And the last example is a little different because, one, I changed this to use a Q abstract table model versus Q standard item model. And also, I am fetching the records in batches, excuse me. I'm not selecting them one at a time. Selecting them one at a time means that I would be doing 100,000 trips to the database. If I fetch in batches in the thousands, I can reduce that to 50 and under. And in many cases, if you're not dealing with a database that has hundreds of thousands of records in it, you can just fetch them all at once. But I'll show you how this works. Oh, excuse me. First thing I need to do. Here is our batch table model, which is based off of Q abstract table model. Again, this code is a bit of a pain, so I'm not going to go through all of this in detail, but everything else in this program is exactly the same. So when we run this, Actually does load a little bit quicker. And that's because I'm fetching them in batches. So one of the things you might ask is, well, how big should a batch actually be? Well, it's going to depend on a couple of things. And unfortunately, it depends on a lot of things. One of the biggest things is how much can your system handle, the PC running the application? Because in my case, my PC is a bit of a monster. So let's say I go back up here and I do fetch 100,000. I'll just fetch them all. You see, in my case, no problem. I took 100,000 records and I gave it to the QAbstract table model and it put them in there without a problem. It clears instantly and they almost show up instantly. But here's one thing, and this is something I want to show you. I did a little bit of a memory comparison between QAbstract or QStandard item model and QAbstract table model. Filling this same 100,000 records, the total memory cost when using QStandard item model was 555 megabytes. When I use QAbstract table model, exact same records, 100,000, it's 89 megabytes. So that's why if you're really memory conscious, if this table had 200,000 records in it, the QStandard item model would use over a gigabyte of memory. This is 555, so you'd be over a gig. The QAbstract table model, you'd be well under 500. So it's kind of a no-brainer to use the QAbstract table model. It's just a pain in the neck to set up, at least in my humble opinion. Oops. All right. So some people have asked me in the past, what do I set the batch at? Well, a lot of times I tell people, go ahead and make the batch size configurable. So that way, if somebody is running it on a much slower PC, they will give their GUI thread enough time to process the records that are being given to them. If they're on a monster like I am, then go ahead and let it pull in the entire table. Like in this case, it's just pulling in the entire table without any problem. There is one last thing I'm going to show you about that. And is it in my Qt testing? I think it's in my Qt testing. Oh yeah, it is. Is it table one? No. I thought I had this open. Yes. This is not threaded, by the way, but this is employing something in QAbstract table model between the two. It's doing something called lazy loading. So if I go ahead and run this, you'll see it opens up instantly. And the reason it opens up instantly is because it only grabbed a handful of records. Now I want you to pay attention to my scroll bar over here. It might be hard to see. It's right here. Watch what happens when I get towards the bottom. Boom, it jumped. That's because it fetched the next batch of records. Now, you may think, well, why is that so important? Well, when you've worked at some of the companies I've been at, our databases have got millions of records in them, not just a couple 100,000 or 1,000 or something like that. They've got millions. One of my friends works at a very big corporation. They have got database tables where 6 billion, over 6 billion records is very common. So if you were trying to scroll through all that or load up all that, you'd be sitting here waiting for 5 minutes. So once you start getting into the millions of things, then you have to start incorporating things like lazy loading, where see, it's just bringing in a chunk at a time. And of course, you can always start by filtering the data ahead of time and that type of thing. But the main point to this, stop complaining about errors. The main point to this is it's a cooperative process. So I have got a worker running in the background. I've got my main GUI thread running. The two need to cooperate with each other. So the worker can't just bomb the GUI thread with stuff and expect for it to keep up. Especially if you're on a lower end laptop or something like that, you may run into all kinds of problems. So it does tend to be a balancing act. And the reason I created some of these got yous in some of these is to show you that that happens. Threading is not an instant solution to the problem. Now, in example one, it sure was, but you got to remember, we're not doing anything very complicated in this example, just doing the counter. When you start getting into more expensive things like database operations, pulling in all that data, performance and memory footprint become a factor as well. Well, I think that's all I've got for tonight. I hope that you found this useful. If you're new to Qt, new to threading, I hope you got a lot out of this. Any questions, please let me know. And other than that, folks, happy coding.